Let us talk about counters. We'll talk about asynchronous counters here. Let us have an introduction of counters first. A counter is a register that goes through predetermined sequence of states upon the application of clock pulses. There are two types of these counters: asynchronous counters and synchronous counters. So what are asynchronous counters? They are also termed as ripple counters. So the clock signal CLK, as represented by clock signal, is only used to clock the first flip-flop. Remember, only clock signal to the first flip-flop, while each flip-flop except the first flip-flop is clocked by the preceding flip-flop. So clock signal only for the first flip-flop. And what are these synchronous counters? The clock signal is applied to all the flip-flops, right? Here first flip-flop, here all flip-flop, which means that all flip-flop share the same clock signal. Thus, the output will change at the same time. Now, the modulus or mod, what these terms mean in this modulus counter subject. So the number of states it counts in a complete cycle before it goes back to the initial state. Okay, so the from initial it goes somewhere and then comes back. This is the number. This is the number of state it follows. This is the modulus. Thus the number of flip-flops used depend on the mod of the counter. For example, mod 4, it uses 2-bit because 2 to the power 2 is 4, while mod 8 it will use 3 flip-flop, that is 2 to the power 3 is 8. So this is how mod 16 will also contain a 4 flip-flop. For example, we have mod 4 ripple asynchronous up counter. Now let us get down to asynchronous counters. This asynchronous or the ripple up counters and they essentially mean, there are down counters also, that we compute, or the number is computed from low to high, means 1 2 3 4 to say 8 or 7, while in down counter the number is computed in a descending order, means 7 6 4 7 6 5 4 3 2 1. Okay, so a synchronous counter that counts 4 number starts from 0 0 0 1 1 0 1 1. Now this is decimal. In decimal this is 0 1 2 and 3, then it again goes back to 0 0. This is called the mod 4 ripple up counter. So this is the next state table and state diagram. This is the present state 0 0, and what is the next state? 0 1. For this 0 1, this is the previous state and this is the next state. For 0 1, this is the next state. Okay, for 0 1, this 1 0 is the next state. For and likewise we have 1 0. This was, if this is the present state, then 1 1 is the next state. This is mod 4 asynchronous up counter. This is a JK flip-flop. Because this is mod 4, we are using 2 flip-flop. One is this JK. Again this is a JK. We have a set and clear. Along with this we have a clock. Now please observe carefully, the clock is only applied to the first flip-flop, and we have made this as high, made J and K as high. Also we have made this, the output of Q, as the input of the next flip-flop. Okay, the output of Q is, because this is going to guide how this will react, what will be the number here. Okay, this is JK high, this is JK high. We are saying that we are passing 1 here. So a 2-bit synchronous, or rather asynchronous counter is shown here. The external clock is connected to the clock input of the first flip-flop. This flip-flop 0 only, So this flip-flop changes state at the falling edge of each clock pulse. This round is for negation, means falling, and this triangle is for edge, so falling edge. So the state will be changed only in the falling edge of each clock, but this FF1, this flip-flop 1, changes only when triggered by the falling edge of the Q output of FFQ. Whatever the output is, this particular flip-flop is not dependent on this clock, it is only dependent on this. So it will follow, the timing diagram will follow the timing diagram of Q. Okay, so note that for simplicity, the transition of Q0, Q1 and clock in the timing diagram shown simultaneously, even though this is an asynchronous counter. Actually there is some delay, we are just showing it for the sake of convenience, but there is a slight delay between this clock Q0 and Q1. So let me just show what happens here. This is a clock, okay, this is falling edge or negative edge triggered. So only at the falling edge, at this point, at this point, at this point, at this point, and at this point, something will happen. On where will it happen? At this point, Q0, because only clock is connected to Q0. So let's make the timing diagram of Q. See, falling edge, let us assume that it is coming to 0, and as the edge goes down, it becomes 1, it becomes high, because we have given high input here, so it becomes high, and it remains high till this point, when again the falling edge is encountered. And again it goes to 0, then again waits for the falling edge, and once it encounters the falling edge, again it becomes high, Q0 high. So this is how Q0 will react to this clock pulse depending upon the input given. Now what will happen to this output Q1? Q0 is what we have achieved here. What will happen to Q1? Q1 will remain at its initial position, but it will see where Q0 is, Q0 timing or clock or whatever you say, frequency, it goes down. So here it goes down, so Q1 will go up. Okay, so again this Q0 is going down at this point, so this will change the state. Q1 will change state only at the falling edge of Q0, this and this. So it falls here, and this is how the final output will be. So again, because of the inherent propagation delay, there is through a flip-flop, the transition of the input clock pulse and the transition of the Q output of FF0 can never occur at the same time. This can never happen at the same time. Therefore, the flip-flops cannot be triggered simultaneously, producing an asynchronous operation. So a 2-bit ripple counter circuit has 4 different state. This is, if you talk about this edge, we have some 0 0 1 0 1, and we have 0 0 1 1. Okay, this we are going to take this 0 0. If we combine this 0 0, Q0 and Q1, the decimal equivalent is 0, and if we combine 1 and 0, the decimal equal to 1. This and this combine, we combine it decimally, so this will be 2, this will be 3, and this is again 0. So you see it goes from 0 1 to 3 and again go back to 0. So this is how the counter works. So a 2-bit ripple counter circuit shown has 4 different states, each one correspond to a count value. These are the count value, and similarly a counter with n flip-flops can have 2 to the power n states, 2 to the power n. The number of states in a counter is known as its modulo number. So this is modulo 3 or modulo 4, and it will count up to 3. 2 to the power n minus 1, 2 to the power n is 4, and 4 minus 1 is 3. It will count till 3, and this is modulo 4 counter. Okay, thus a 2-bit counter is a mod 4 counter. Usually all the clear inputs, these clear inputs are connected together so that the single pulse can clear all the flip-flop before counting starts. This all will be cleared. So the clock pulse fed into this flip-flop is rippled through the other counters after propagation delay, like a ripple on water, hence the name ripple counter. How is this? This clock goes here, then the output goes here. If any other flip-flop is there, the output goes here. So it is kind of rippling effect. Okay, that is why we call it as a ripple counter. So a mod n counter may also be described as a divide by n counter. This is because the most significant flip-flop, the furthest flip-flop from the original clock pulse, produces one pulse for every n pulses at the clock input of at least of the least significant flip-flop, the one triggers by the clock pulse. So once we trigger here, then the ripple will go, and this is how a module n will be computed. And in the similar fashion, the asynchronous up counters can be made for mod 8. For mod 8, you require how many? 2 to the power 3, means you need 3 flip-flops. This is a JK flip-flop. Again, we have made it high, made JNK high, all 3 high. Then this is a clock pulse. This clock pulse goes to the first flip-flop, and the output of this, see the Q bar, goes to the input of this. This acts as a clock for this. Again, the output of Q bar for the second flip-flop goes to the input of the third. And this Q0, this Q1 and Q2 will be the values which are coming is of our interest. So the following is a 3-bit asynchronous binary counter, and the timing diagram is for the 1 cycle. It works exactly the same way as 2-bit asynchronous binary counter mentioned earlier in the slide, except it has 8 states because of the third flip-flop. Let me just go through it. These are the clock. Okay, so now because we don't have a 0 here or around here, we can very well see this is a positive edge triggered flip-flop. So clock is coming. This Q0 will result only when we have a positive edge, going up edge, going up edge. Only at this point it is going to affect. So at this point, let us start with 0. And when it encounters clock up or going or elevating edge, this will change state. Again here it will change state. Here it will change state. Here it will change state. Maybe 0 to 1, 1 to 0. So at every uprising edge, the state will be changed. So this is the timing diagram of Q0. Now we will remove it. Now we will ignore it, because this Q1 will only depend on the input which we are getting from this Q bar. So let's see at this going down edge or this falling edge. At falling edge, Q1 will respond because the Q bar is connected to this. If Q0 would have been connected to this, the second flip-flop, then this Q1 would have resulted or would have reacted in the positive edge. Okay, but now this Q bar has been given, so this will be resulting, or the effect will be taking only when Q0 has a falling edge. So at every falling edge it will change the state. And again the same version goes for Q2 also, because Q2 is only dependent on Q1. Okay, now you can find out the values here at this point, at this point, at this point. See here what we have 0, we have 1, and we have this 0, so this is 2. So at each and every point we can compute the numbers in decimal, and we find that it goes from 0 to 7 and again goes back to 0. This is a mod 8 asynchronous counter. So these are the state. We have 0, 1 up till 7. These are the states, and I described you in detail how it takes place, how the numbers become from or takes place depending upon the timing diagram, depending upon the clock, only for the first flip-flop, the resultant of the flip-flop is to the second and to the third. This timing diagram values will give rise to these states, which we call as modulo 8 asynchronous counter. So this is modulo 8 asynchronous up counter. Similarly, if you want it to be up, you just have to place a 0 here. There is no much difference. You just have to place 0 or a round or circle here, because it is because this A is going to take effect only at the falling edge, not at the rising edge. So this is modulo 16 asynchronous up counter. Now we have got down to mod 16. Mod 16, we require how many? 2 to the power 4, that is 16. 16 means 4 at least. We need this flip-flop to make a mod 16 counter. This is again a up counter, negative triggered, right? Let us see this input is clock, the output of Q is given to this second flip-flop, then likewise this is the rippling, this is the rippling, this is the rippling. We have some VDD, means we are giving one logic to JK everywhere. These are the outputs we are taking: Q0, Q1, Q2, Q3. This is Q0 is the most significant bit, Q3 is the least significant bit, and now the clock because this clock will only give rise to any action only to Q0. So Q0 is dependent on this clock. So let us see. At this point, I'll just show you one or two. At this point, at this edge, which is rising, the state will be changed to 1, and at every rising edge the state will be changed. Now we'll remove or ignore this. Q1 is dependent on Q0, so Q0 wherever it is falling edge, because we have a this negative triggered this clock, essentially a clock, because Q is acting as a clock for this. So this is a negative edge. So at falling edge, this Q1 will remain to 0, and at this falling edge it will become 1, and will change only when we have a falling edge of Q0. Again, Q2 is dependent on Q1. So again we have a falling edge because of this negative triggered. This particular action will take place like this, and similarly for Q3. All these values 0 0 0 0, 6 0 0 0 0, this is 0 0, then 1 0 0 0, you take it will be 1, and likewise you will finally at certain point after 14 because this is 16, after 15 numbers or 15 cycles you will be reaching 1 1 1 1, that is your 15, because 2 to the power n minus 1 maximum number can be counted. This is 15, and again on the next any cycle this will become 0 0, and this whole diagram, this timing diagram, will be repeated. So if we talk about a positive triggered, would you know what to do? You just have to remove 0. And this asynchronous down counter, because you want now to count from not from 4 or 3 starting from 0. Now you want it to be computed from 0, say let us relieve 0, 3210, 3210, right? Means if we have a 8-bit counter or mod 8 counter, it should start from 7. If we have a mod 16 counter, it should start from 15 till 0. What you have to do is, this is A, this is the LSB, and this will be the MSB. Okay, this will be the MSB, this is B, this is the LSB, and one logic is provided to JK. Rest all remains the same. The clock will be given to CLK. The output of Q will be given to this C clock, to this flip flop. Only A will be considered as what? LSB, and this B will be considered as the MSB. So 1 1 it becomes 3, 1 0 it becomes 2, 0 1 becomes 1, 0 0 becomes 0. Again you compute, it will be a asynchronous down counter. So asynchronous counters, if mod is not equal to 2 to the power n, so far actually we have designed the counter with mod number equals to 2 to the power n, where n is a number of bit, n 1 2 3 4. That is why we have made counter for mod 2 to the power 2 is for mod 4, mod 8 and mod 16. This also corresponds to the number of flip-flop. Thus the counters are limited on for counting mod 2, mod 4, mod 8, mod 16. The question is how to design mod 5, mod 6, mod 7, mod 9, which is not a mod 2 to the power n or counter. Okay, what to do with the mod 6? The mod 6 counter actually will be counting from 000 to 101, that is 0 to 5, and after that it has to bounce back or recount back to 0 continuously. So asynchronous counter, which is not the fixed counters which we design. So this mod 6 ripple counter will be made like this: 0 to 1, 1 to 2, 2 to 3, 2 to 4, and again to 0. So the states will be like this: 0 0 0 to 0 0 1, because this is 0 0 0, 0 0 0 0, this is 0 0 1. So the next state will be written here and the present state will be written here. So at this point it has to become 0. So the circuit diagram for mod 6 ripple counter up counter will be like this. Okay, what changes we have done, what things we have changed? We have JK flip-flop, 1 flip-flop, 2 flip-flop, and then a 3 flip-flop. Again the clock, this is a negative edge triggered, negative edge triggered, negative edge triggered. But the output is MSB of C, the output of this B, these are ANDed, converted or inverted, and again given back to this reset. Why? Because at this point 101, we want at certain point where it is 101, it has to go to 000. So by employing this particular logic, detect the output at CB A equal to 110. Okay, to activate, because to activate clear we need to clear it. So NAND gate is used to detect output that generates 1, which is going to number or which values are going to give result as 1. It will be 110. Okay, so 1110 will give at this point we want it to be cleared. So let me reiterate it, that this NAND gate is only used to find out which of these two values will present a 1, because we have used a not here. So whichever value is given here, because we want this 110 to be 0. Okay, 110 needs to become 000 to finally reach 001 again. So we are finding 110 as 110, means this is not to be taken, only 10. If this is taken, this will take the value and gate and will clear the flip-flop, and the counter will run again. So this is how simple it is. So asynchronous decade counter is also there. We have a binary counters previously introduced. We have 2 to the power n state, but counters with state less than this number are also possible, as we have just seen. So they are designed to have the number of states in their sequences, which are called truncated sequence. These sequences are achieved by forcing the counter to recycle before going through all of its normal state. If we don't recycle, it will go up to either 4 or you say 8 or to 16, or how many flip-flops you have used, but we need that it needs to be recycled. So common modulus for counters with truncated sequence is 10. So counter with 10 state in its sequence is called the decade counter, modulo 10 counter. The circuit is the implementation of decade counter. So what we have done is, it is essentially the same, everything is same, only the output from here and output from this Q, this Q1 and Q3 is taken here, they are made as NAND, and finally the reset has been done. So this is how if we reach 1001, we want again to code this back to 0000. The sequence of decade counter is this. So when the counter counts to 10 means 1010, all the flip-flops are being cleared. Okay, so notice that only Q1 and Q3, this Q1 and Q3 are used to decode the count of 10. This is called the partial decoding. As none of the other states 0 to 9 have both Q1 and Q3 high at the same time. So whichever is high, because see, this is which one is high, whichever is high we will use it. Q1 and Q3 are high here at this particular point, so we are going to use it. See, we are only using Q1 and Q3 because at that particular point where it becomes 10, we just, this is Q0, Q1, Q2 and Q3. So Q1, okay, Q1, Q3 we will take and just NAND it. We are making it NAND, okay. That is why we are taking this Q1 and Q3 only, and once they are applied, we can finally find out that this is the modulo 10 counter. So in certain application, a counter must be able to count both up and down. So the circuit here is a 3-bit up down counter. It counts up or down depending on the status of the control signals up and down. So we have a down, we have a up. Okay, this is also introduced. So when the up input is at 1, this input is at 1, and the down input is at 0, the NAND network between FF0, this flip-flop 0, and flip-flop 1 will gate the non-inverted output Q of this F for first flip-flop into the clock input of what? Second flip-flop. Similarly, Q of FF1 means Q of flip-flop 1 will be gated through another NAND gate, this another NAND network into the clock input of FF, where FF2, this flip-flop. See, this is one logic, this is one logic. So the counter will count up or down depending on the whether up is high or down is high. So when the control input up is at 0 and down is at 1, the inverted output of FF0 and FF1 are gated into the clock input of FF1 and FF2 respectively. So if the flip-flops are initially reset to 0, then the counter will go through following sequence as the input pulse are applied. Okay, this entirely depend on the up is high or down is high. This logic will compute in a up manner or a down manner. So notice that an asynchronous up-down counter is slower than an up counter or a down counter because of the additional propagation delay introduced because of these NAND networks. So asynchronous up-down counters waveform for 4-bit up-down counters. This is the up count sequence. This is the down count sequence. So disadvantages of asynchronous counters are propagation delay is severe for large amount of counters, especially at the MSB, and existence of a glitch is inevitable for mod which are not equal to 2 to the power n counters. So it cannot design random counters, that is to design circuits that counts number in the sequence 5, 6, 7, 2, 3, 1. Okay, you have to go to ascending or a descending with the difference of 1. If you want some random numbers, you cannot. So the solution is synchronous counters. We'll see this also. Thank you so much. Take care.